We are going to continue on with our introduction to statistical mechanics. To start things off, we're just going to go over a few definitions. Then we are going to hopefully derive the Boltzmann distribution, which is related to the kinetic energy distribution as a function of temperature. So, the first thing to look at is, remember, the idea behind StatMech is that we're going to take a set of rules about how individual particles behave and then scale it up to an arbitrary number of particles. So the objective then is to translate from effectively ideas and hypotheses about how molecules behave, and then calculate macroscopic thermodynamic properties, assuming that you have an ensemble or a statistical average. So I'll use that term ensemble quite a lot, meaning that you have enough particles and enough configurations that effectively represents the system. So we'll talk about what that means, which is effectively your ergodic hypothesis. So really quickly, let's just look at particle in a box. So particle in a box from quantum mechanics is actually going to be scaled up to become our ideal gas law. Right? Because what we're doing in the ideal gas law is effectively saying that we have a collection of particles that don't interact. So that means the total energy of an ideal gas is going to be the energy of an average particle times by the number of particles. So in a sense, quantum mechanics particle in a box is exactly the same thing as an ideal gas. Right? And we'll show that over the course of the next couple of lectures. So the energy of a particle in a box is a function. Again, we're going to rely a little bit on quantum mechanics. We can do all of this with classical mechanics, but we might as well just insert the quantum while we can. We don't have to know the quantum, we just have to know how to apply its conclusions. So the energy of a particle in a box is going to be a function of individual quantized numbers, in this case Lx, Ly, Lz. These are going to correspond classically to the velocity in the x, y, and z direction. So the conclusion for a 3D particle in a box, we have Planck's constant. So these are integers, 1, 2, 3, 4, 5. This is Planck's constant, this is the volume of the box, and this is the mass of the individual particle. So, what we're going to be using this as an example for is to talk about the difference between energy states and energy levels. So the objective of quantum mechanics, through the ergodic hypothesis, again, I'll recap that in just a moment, is that if we can calculate all of the states, or we can organize all of the states, that is the way that we can unlock the translation to the macroscopic scale. So, I'm going to write out 3 different energy states for the particle in a box that'll all have the same total energy, or what we call the energy level. So we can write this as a function of the quantized parameters, right? So let's say, for example, we have an energy state where the particle in a box has an Lx of 1, an Ly of 1, and an Lz of 2. That means that the energy level of that system is going to be proportional to, in this case here, 1 squared plus 1 squared plus 2 squared, which is going to be 6, right? Does that make sense? We can also have another energy state which is distinct, 1, 2, 1. It's going to have the same energy level. It's going to be proportional to 6. All these kind of messy coefficients right there. And we can have a third one, 2, 1, 1. That's going to be proportional again to 6. So some of the nomenclature that we're going to be discussing. In statistical mechanics, we are going to have distinct energy states that all have the same energy level. And in this case here, for the energy level of whatever 6 is, whatever it works out to be, this energy level is proportional to 6. It has a degeneracy of 3. So what we're going to call this is that omega is equal to the degenerate, well, okay, maybe I can spell this one right. Okay, degeneracy tells us the number of different ways that we can organize the system where we have the same energy level. Now we're going to use the nomenclature of a capital omega. This is the degeneracy of a collection of particles. So when we are trying to determine the total number of states of the system, we can count up all of the individual energy states, or we can count up all of the different energy levels multiplied by the degeneracy of that energy level. Right, so these are just terms that we're going to have to be comfortable with. Energy state, energy level, and degeneracy. Is it clear what we're trying to define? Right, but these are going to be terms that are going to be popping up throughout the discussion. So, now how this relates to the postulates of stat mech. So one, we have the equal a priori principle or hypothesis. Equal a priori principle or hypothesis, meaning that a priori, does anyone know what that means in Latin? A priori means we have to assume it before we can even start the calculations. So we have to prove it after the fact that it's appropriate. So we have no evidence to support this is appropriate when we start stat mech. Right? We have to assume that it's true, and as it turns out, it gives us really useful predictions. So who's to say whether or not you can say it's wrong? So what we're saying here is that all energy states, in this case here, we have 1, 2, 3 energy states that have the same energy level, which of course these three do. They are all equally probable. Now this is the principle that we are going to be exploiting to calculate the Boltzmann distribution and the canonical partition function. And we'll talk about what that second term means. Hopefully today, maybe on Friday. The second principle of stat mech that we have to sort of accept is the ergodic hypothesis. Now what the ergodic hypothesis states is that, let's see, there's no good definition that I can just quickly write on the board. What I'll write is a really, really brief one. And I'll explain what I mean in a moment here. So, the ergodic hypothesis is basically the tool that we use then to translate between statistical mechanics and the real system. So, in a real system, gas particles are fluctuating their energies, their velocities, their positions. Everything is being resolved as a function of time. Molecules are moving around and tumbling. But that's not at all what we're representing here. What we are representing is a static state of the system. We're saying, boom, freeze all the particles. I'm going to count up how many particles have particular states. I'm going to calculate their energies, and I'm going to use this information, right, in order to calculate how the real time average system is. So the ergodic hypothesis is basically what allows us to take all the calculations that we're going to be doing in class, which are going to be statistical averages of the system, and relating it to the real world, which is actually a time-resolved average. So when I stick a thermometer into a glass of water, what I am measuring is a time-averaged collision of those water molecules with the thermometer itself. That's what I'm actually measuring. But through the derivation of the Boltzmann distribution, what I'll be doing is actually taking a statistical average of the probability of the system being in a particular configuration. So one of the easiest ways to visualize this is through thinking about different types of simulation methodologies. Who's heard of molecular dynamics? 2 people, 3 people. Who's heard of Monte Carlo simulations? A few more people. Okay. So what happens in molecular dynamics? Molecular dynamics. We have, and I'll just draw it as a 2D simulation. What we will do is we will have a series of particles. Now these particles will have a particular position, and they will have a velocity. Now this velocity of the particles is going to be related to the temperature. Now from a classical perspective, we don't know that. But we've all sort of gone through years worth of thermodynamics, we all know what molecules are. But the Boltzmann distribution is what allows us to know that the temperature is related to the kinetic energy of the particles. So if we have a chance, if we get to it, we'll get through that derivation today, but it's kind of a lot of work to get there, so we might not get to it. So we have a collection of particles with velocities corresponding to the temperature of the system. How we do a molecular dynamic simulation is we then allow the particles to move a little bit, and then consider a new configuration of the system. All right, so this particle moved very quickly up here, all right? Maybe it hit the wall and it's bouncing back this way. This particle moved a little bit in this direction, didn't hit anything, and this particle moved over here and it's about to hit the wall. Right, that's an entirely new configuration of the system. We're watching the time-averaged evolution. Now let's repeat this process again. Come up with a new configuration. Repeat the process again. Come up with a new configuration. Now let's imagine that every single one of these delta t steps is significantly far that the position of the previous step is uncorrelated with the new one. What we can do then is we can build a bigger system. So I'll call this A, B, C, D. Okay? So I've taken my time-resolved results in a simulation, and I've kind of stacked them together to make a bigger box. And this is totally appropriate because these are all going to have the same energy, they're all going to have the same number of particles, and they're going to have the same density. So when I stack them all together, the average energy, the average temperature, the average density is all going to be the same. So what I can do then is I don't have to simulate a billion, million particles to simulate the properties of a glass of water. I can take a significantly smaller system and run it for a long time until I can build a bigger system where the properties are homogeneous. This is the time averaged. This is what's really going on in the real world. This is how the molecules are transporting and moving around. Now in contrast to that, a Monte Carlo simulation is the computer equivalent of what we're going to be doing on pen and paper. So stat mech was developed before we even had computers, right? This is in sort of like the late 1800s, early 1900s, right? The first computers didn't come on until maybe the 1930s, maybe the 1940s, right? So we had no tools to actually do automated calculations. So everything was done by hand, by slide rule. So in a Monte Carlo simulation, instead what we're going to be doing is we're also going to be developing 4 different boxes. Oops, and I ran out of space, so I'll put this one up here. But we're not necessarily going to know what the velocities of the particles are at all. What we're going to be doing is we're going to start off with an initially random configuration. Then what we will do is we will take one of these particles and we will magically just move it to a different position. Now whether or not we accept this movement is going to be based on a Boltzmann factor for the NVT ensemble. This is called the Metropolis algorithm. So the reason why we can do this, we don't know why we can do this because we haven't quite derived all of our principles of stat mech yet. But then we say, okay, if this move lowers the energy of the system, that's fine. We're trying to find the lowest energy equilibrium configuration. If it doesn't lower the energy of the system, sometimes we will accept it, right? Because in the Boltzmann distribution, we have a probability distribution of different energy states. So as long as we follow the probability distribution of the Boltzmann distribution, we're going to be adhering to classical thermodynamics, or even statistical thermodynamics. So let's say this move reduces the energy. That means we have another state like this. We're going to take this particle, we're going to move it here. Oops, put a dash line. Up. This one, again, in this case, probably wouldn't reduce the energy, but let's just say it does. And then we could have another one, right, with a different configuration. So we're not actually following any of the laws of physics whatsoever about how the molecule is really, truly dynamically rotating and tumbling around through the system. But instead, each of these configurations are acceptable configurations of the system. So what we do is then we do exactly the same thing, where we add them in a tiled sense. So we say A, B, C, D. Now, if we do this enough times, we will have an ensemble average if we run the molecular dynamics simulation enough so that the properties don't fluctuate as a function of time. We'll have an ensemble average of the Monte Carlo if you take enough statistical movements as well. This is the ergodic hypothesis, meaning that if we are trying to predict macroscopic thermodynamic properties, we can either follow the time averaged approximation of Newtonian or quantum mechanics, Newtonian physics, or non-Newtonian physics, or we can move the particles around arbitrarily until they have sampled all of the possible configurations of the system. Without the ergodic hypothesis, we cannot do statistical mechanics. What we're going to be doing, instead of letting the computer do all the work of guessing and checking and moving the particles around, we're going to be doing that by hand and basically saying, if the particles behave this way, these are all the configurations of the system. But this is one of the most important principles, I think, to understand whenever you look at a theoretical paper. When you're doing your research, do not shy away from simulation work, because there's a lot of it. I would say, I don't know, 30% of all research papers are probably simulation based, just because they can write a lot of them. And they do have a lot of good. But oftentimes, the papers don't necessarily demonstrate that they're ergodic. If they're non-ergodic, that means that they don't have a guarantee that they're actually at the equilibrium of the system. That doesn't mean that the simulations are necessarily wrong, it just is not as safe of a bet. So this is a really important principle. Does anyone have any questions about the differences between these simulation tools? But this is kind of the modern thermodynamics. Okay. So what we're going to do now is we are going to more or less exploit the equal a priori principle to demonstrate what its consequences are, and in the process we'll be deriving the Boltzmann distribution. This is Dynon. Does anyone know roughly what the Boltzmann distribution looks like? Kind of looks like this. So it basically says that there's an average energy that is the most probable in the system. But that means you also have some particles with really high energy and some particles with really low energy. So when you see a curve that kind of looks like this, where it goes up, then it goes down, that generally means that you have two competing effects. One that increases, and then one that decreases. And then the contribution of those two leads to a maximum. So in the case of the Boltzmann distribution, as sort of a preview of what's going to be occurring here, is that in this region right here, as the energy goes up, the number of states goes up. But as the energy goes really, really high, the probability of being at that energy drops very, very quickly. So what the Boltzmann distribution basically shows us is that it's a balance between the number of statistical configurations of the system with the decreased likelihood that the system is going to all be at a very, very high energy state. That's in essence what the Boltzmann distribution demonstrates. So how we derive it is we build a box, just like how we did with classical thermo. We will have two subsystems A and subsystem B. This is going to be an infinite reservoir. So subsystems A and B are both at the same conditions. We'll see later on when we connect this to classical thermodynamics that this will correspond to the temperature. But in the derivation, we don't actually have to assume that that necessarily relates to the temperature. But from using classical thermo, we can basically say that A and B are at the same temperature, but they don't communicate. They don't exchange particles, they don't exchange energy. They only exchange energy with the reservoir itself. So the nomenclature that we'll adopt is that P of A, meaning that the probability of subsystem A being in some state with energy E of n. Okay, so this is going to be probability of system A in microstate with energy Likewise, we have probability of system B being in a state with energy EM, so this is probability of B in microstate with energy EM. Now, we don't have to worry necessarily if this is the microstate, sorry, the energy of the energy state or the energy of the energy level, because it's the same probability. All energy states have the same probability. Okay, equal a priori principle. Someone took the dry erase marker. This is a chalk marker, which as it turns out does not work very well for dry erase boards. Okay, so if we combine these two, the probability that system A is in a state with energy En multiplied by the probability that system B is in a state with energy Em is going to be the same thing as the combined system of A and B being in an energy state that is the combined energy. Right, so we can kind of think of this like, I don't know, what is the probability that box A has, you know, a red colored ball, and the probability that box B has a red colored ball? And then multiply those two together, gives you the total probability that the combined system has some property. Make sense? So, what we'll do then is state that we'll do a little bit of math, and this is kind of similar to how we did a lot of derivations on the classical perspective. We will take a small deviation in energy of subsystem A, holding the energy of subsystem B constant, of the combined probability. This is kind of similar to how we did thermodynamic identities type thing. So we can write this out. I've expanded it a little bit using, what is this one, the product rule, I think. Right, so these two top terms would cancel out. Chain rule product, I can't remember which one it is. Chain rule. So this term here actually goes to 1. The rate of change of the energy of N with respect to energy n goes to 1. Em is independent from En, that goes to 0. So this derivative right here simplifies to just this term. Goes to 1, yes. All right. Now what we're going to be doing, so we took the partial derivative with respect to this side, we're going to take the partial derivative with respect to the other side, because we know they're equal. So this one here is the chain rule, right? Did I get this one right? I think I got this one right. Or this is the product rule. This is the product rule. Yeah. My notes are wrong. Yeah, I wrote chain rule here in my notes. This is product rule. So it's, derivative of first times the second, derivative of second times the first. However, the probability of subsystem B, depending on the energy of subsystem A, is 0 because they're not connected in any way. They're only connected through the reservoir. So this one simplifies to just these terms here. So we can set these to be equivalent such that we have we're getting close. Okay, so we can repeat everything that we just did, but just switch E and M. Sorry, N and M. So this part right here, obviously it doesn't matter if we switch the order of those two. This is still going to be equivalent. So what that allows us to do then is then just basically repeat this procedure, but swapping out whether or not we did it for subsystem A or did it for subsystem B. So in this case, we can find that the rate of change of the probability of system B being in state EM with respect to EM multiplied by probability of subsystem A being in state of EN. So this is the equation that we're going to solve now. So all we've effectively done is apply the equal a priori principle, saying that the probability of the system being in some state is going to be related to the energy of the system, and that if all the systems have the same energy, they're going to have the same probability. This is just a mathematical, clever way of doing that. Who remembers their partial differential equations? How do we solve this one?
Separation of variables.
Bingo, separation of variables. So let's get all the A stuff on one side, all the B stuff on the other side. So we have 1 over PA. This is the same little trick that we've did lots of times with the Clapeyron equation. When you see something like this, we can then rewrite it as maybe equal to some constant. This is our separation of variables. This is one of those really fun derivation days in class. Now I've chosen this constant beta This is the common nomenclature that we use in statistical mechanics. When we do relate our final equation, we will find that beta is equal to the inverse of temperature scaled by the Boltzmann constant. So oftentimes it's just easier mathematically, instead of dealing with the reciprocal of temperature, to use this beta parameter. I don't know if it has a name. I've always just called it beta. But, so the rate of change of the probability of the subsystems A and B is basically going to be related to the system temperature. But we won't know that until we do the comparison. So, if we solve this equation, you should recognize that this is an exponential function. Or those of you who are keen on your differential equations. So in this case, the probability of subsystem A existing in state En is equal to a constant of integration times by this probability of system B being in system M. And at this point, we don't really have to consider A and B at the same time. We'll just focus on A. All right, so just to recap how we got here, the starting point was effectively here, taking advantage of the equal a priori hypothesis. If there's a probability of system A having some energy state En, probability of system B having an energy state of Em, you multiply those two probabilities together, right? So you can kind of think of it as like, let's say this is a number between 1 and 10, this is a number between 1 and 10. The probability that the system has a number between 1 and 100, right, would be, these two multiplied together. Kind of a similar idea. Okay. Then we just sort of manipulated it through a little bit of calculus. Went through the process of doing separation of variables, and we derived this term here. So, in order to get the constant of integration, we know that the summation of all the probabilities has to equal to 1. The system has to be in some state. Which gets us to the conclusion that the constant of integration all the states N or En, is we basically just add all of these ones up, so it has to be the reciprocal of that. Right, so this is adding up all the different states of the system. I think we might get through this. Kind of skipping over some of the math details. So, we now define a new function. We define this function called Q, and we call it the canonical partition function. The canonical partition function is equal to basically the denominator. So in statistical mechanics, the partition function is what our objective is. The partition function here is the summation of all of the states of the system. In this case, it's scaled by something that we call the Boltzmann factor. So this e to the minus beta e, or energy, I said e twice, that's what we call sort of the Boltzmann factor. The higher the energy of the system, the lower the probability it's going to be in that system. And that gives us the second half of the Boltzmann distribution. The higher the energy of the process, the lower the probability. And so when we relate this back to that Monte Carlo simulation, when I take a movement of a random particle and move it to a different location, if that new configuration has a high energy, that means it has a low probability of existing. So we use a random number generator to see if we have a reasonable probability of having that. But the partition function will show, hopefully today, that this gives us access to all of the thermodynamic properties of the system. Manipulating the partition function gives us everything. The partition function in itself is not particularly useful. How we manipulate it is going to give us access to the thermal properties. So that means that the probability of, let's say, subsystem I existing in some energy state with E alpha is going to be equal to some scaled property of the energy, the Boltzmann factor, over all of the individual states for I. Which is equal to the Boltzmann factor over the partition function. So in this case here, as the temperature increases, that means the coefficient beta, which again, we don't really fully know this connection, but I'm telling you, this is how it is. Beta goes down closer to 0, which means then that e to the minus beta ei approaches e to the 0, which gives us a probability of 1. Or rather, the numerator is 1. So what this conclusion tells us is that as we increase the temperature, the system doesn't go to the highest energy state. At high temperatures, energy becomes irrelevant and entropy takes over, which means that all states are equally probable at elevated temperatures. Because if you think about it, if you increase the energy and increase the energy and increase the energy, if all the particles went to the highest energy state, we would be decreasing the entropy of the system. So at infinite temperature, all states are equally probable. That's one of the conclusions here. All right. So, how we get to the Boltzmann distribution here is I'll just slightly rewrite that expression. That is the summation of over all the states. So instead, we can write instead of it being an energy state, we can say, what is the probability that the system has an energy level equal to E alpha, which means that this is going to be the degeneracy of the energy level E alpha multiplied by the factor that we just derived, divided by the partition function. Remember, this is just the summation over all of the states. So, as the energy increases, the degeneracy should increase. The number of ways that you can sort the system out will increase. Now, how it increases, it depends on the model of the system you're using. But proportionally, as your energy level increases, the probability of being in that state goes down. These are the two competing effects that we have. So Boltzmann derived this distribution using only classical particles, meaning that the energy of the system was only the kinetic energy of the particle itself. So I know we started things off with quantum mechanics, but we didn't have to do that. So we're going to say that the energy of some state I, or energy level, is going to be related to the magnitude of the velocity. Such that the velocity vector is going to have its sort of resultant components, I think is the term. I don't have my vector terminology quite ironed out quite yet. So, the number of ways that you can combine Vx, Vy, and Vz in order to get the energy is going to be proportional to the velocity squared. Right, so you're going to have an increase in the number of ways to reach a finite velocity by adding together the individual components. So which means that if we were to look at the degeneracy, this is going to increase proportional to the energy squared. So you're going to have more and more and more and more states as you increase. Whereas the probability right, so if we were to plot this function here, at 0 energy, it equals to 1. As you increase the energy, you have an exponential decay. I think it just drops straight out down. Let's think. I'm sorry, I can't remember if it goes like this or if it just goes straight down. Either way, same conclusion. Now we combine these two together, and we derive the Boltzmann distribution. And this right here is how we can get the average kinetic energy of the system. It's the most probable energy state. Any questions so far? Okay, one last thing to talk about, and how we can relate the partition function here to something useful. So I'm going to go, I'll just do it over here. I'll erase this stuff so I can keep that side of the board open. So we are up to about 1870s research. This is about where we're sitting right now in terms of the mathematical complexity. All thanks to Maxwell and Boltzmann. Okay, so U is the notation that we use for the internal energy of the system. Hopefully that's not a shock to anyone. We're going to call this the average energy of the system. Okay? This is the most probable energy that we would expect based on the Boltzmann distribution, which is derived through the canonical ensemble. So that means that our internal energy is the average energy of the system. Now in this case, we're only considering kinetic energy, right? So this is basically an ideal monatomic gas. We're not considering any interactions. We're not considering any internal modes of storage, right? There's no rotations, there's no vibrations, there's nothing like that. Now to make these models more complicated, right, we would have to rederive effectively the partition function, because in this case the partition function is only focused on the energy, rather here, this contribution, that energy, we're only considering the kinetic energy of the system. Right, so changing the model of the function of the energy will change the conclusions of the thermodynamic properties. So to get the average energy, we're going to add up all the different energy states of I, and we're going to multiply them by their probability. Right, so this is a weighted average of the energy of the system. We substitute in our definition for the probability. In this case, we'll use this definition over here without the degeneracy, because we're adding up over states as opposed to energy levels. And recall Q, right, is the summation over all of the different energy states. So just to write this out very clearly then. Now, this looks pretty similar to a derivative. Particularly, it looks very similar to the derivative of an exponent. Right, when you take the derivative of the exponent, in this case, if we were to take the derivative of this function here with respect to beta, it would just be equal to itself multiplied by that junk up there. So what we can infer then is that the numerator is related to the derivative of the partition function with respect to beta. Right, so if we take this function here, right, since it's a summation, we can take the derivative of everything independently. So the coefficient EI is going to fall down, but then it's still going to be multiplied by e to the minus beta EI. And then we can just factor that out again and then sum them all back up. Right, so this is equivalent. This expression here is equivalent. So that means we can rewrite that the internal energy, which is the weighted average of all the energy states of the system, is equal to 1 over the partition function here, right? This is 1 over the partition function multiplied here by the negative of the numerator, which is this big long one here, which is equal to minus the partial derivative of the partition function with respect to beta. Now again, we're going to use this little mathematical trick, this little calculus trick. Anytime you see a derivative multiplied by a reciprocal, you can make that into this expression. And this is a very important conclusion to statistical mechanics. So, one of the reasons why thermodynamics is a little bit tricky. The math in thermo is by far simpler than fluid mechanics, than heat transfer, than mass transfer, than virtually any other system that you'll ever work with. We never have to take a derivative with respect to time. We never have to watch things resolve. Thermo is almost always a system of equations that we're solving, right? What makes thermo tricky is that when you think about heat transfer, it's very intuitive. We think about a hot surface and touching it and feeling the heat given off, right? We think about convection. Or at mass transfer, we can see, a sugar cube dissolve in coffee. Thermal gets a little bit trickier, right? So on the spectrum of abstract, I kind of view heat transfer and mass transfer over here, and I view quantum mechanics over here. Classical thermo kind of fits somewhere in the middle because we're talking about temperature and pressure. Statistical mechanics fits a little bit closer to the abstract, and then quantum mechanics, we're strictly in the realm of abstract. Right? The wave functions are objective in quantum mechanics, which means basically nothing. Right? The wave function gives us information when we manipulate it. Right? When we take the complex conjugate of the wave function, it gives us the electron density distribution. The partition function is very similar. The partition function in itself, Q, has some physical intuition, right? It is related to a weighted summation of all the different energy states in the system. But the partition function in itself, and this is sort of crazy, once we start putting models in here, you can calculate a number for the partition function. But it's a number that doesn't really particularly have any meaning. Now, where we get meaning out of the partition function is by manipulating it with respect to the variables that it has. Now, in this case, we've shown that the internal energy is related to how the partition function changes with respect to the beta, or the temperature. Right? So as you increase the temperature, you increase the density of states. That's going to increase your internal energy. Now, different partition functions for different ensembles. In this case right here, we've talked about what they call the canonical ensemble, which is a constant number of particles, a constant volume, and a constant temperature. But there are different ensembles for different scenarios. The microcanonical ensemble is constant number of particles, constant volume, and constant energy. It does not have these same relationships. It's an entirely new theory. Now in the microcanonical ensemble, this partition function is directly related to the entropy. In the canonical ensemble, actually, it's directly related to the Helmholtz, but if you take the derivative with respect to beta, that gives you internal energy. So what we're going to be doing in the stat mech derivation is we are going to be deriving these different partition functions, and then as quickly as possible, we're going to be relating them to macroscopic thermodynamics. Right, so what we're going to be doing is now, through the internal energy, we've created a connection between the partition function, which is extremely abstract, to what the internal energy of the system is. Now we can manipulate the internal energy and just simply do a mathematical substitution with the partition function, and then we can demonstrate that there's a relationship between other thermodynamic variables in the partition function. But just as how the Gibbs free energy is the best for constant temperature and pressure, right? In this case here, NVT, which thermodynamic variable is the closely related to NVT? Helmholtz. So in fact, the partition function, the natural log of the partition function, is directly proportional to the Helmholtz energy of the system. When we take the derivative with respect to temperature, dA dt, that'll give us internal energy. But in this case, it's just nicer to just talk about sort of U being the average energy. But the native variables of the canonical partition function are actually Helmholtz. Just likewise, there's the grand canonical ensemble, which is an NPT ensemble. There's lots of different types like this. So, let it sink in for a little bit. I know this is somewhat on the more abstract side, but this is the connection that we need to take to get from the concept of molecules and how molecules behave. But the key thing to take away before I know I've stolen too much of everyone's time, the key thing to take away here now is that instead of us relying on measuring properties of the system, we can instead come up with a model that tells us if we have a collection of particles that obey a certain rule. And I always kind of think of this like a board game or a video game, right? Where you have different characters that have different strengths and weaknesses, right? If we have a way to calculate what's the energy of all of those particles based on their behaviors, then we've taken the abstract concept of internal energy and we've translated it into a set of coherent rules that we can say, oh, so oxygen has a different heat capacity than argon because it has a bond vibration. How do we model the energy of a bond vibration? How do we model the energy of a rotating molecule? In this case here, we've modeled the kinetic energy based on the velocity, rather. Here, we've measured the kinetic energy based on velocity. So now it simplifies our arguments and discussions not to how does this weird fluid behave, but rather how does the molecule behave at the atomistic length scale. So that's the whole objective that we've accomplished by looking at the canonical partition function. Okay, quiz on Friday, not about stat mech, about fluid phase equilibrium. And I will see you all then.
Not the chemical equilibrium.
No, probably not chemical equilibrium either.